Section 1.3 is where we introduce the limit of a function. So this is our first step into calculus. And it'll turn out that the limit of a function is really the heart of calculus. It's how we'll generate things like the derivative and the integral, and how we'll really analyze functions in a really useful way with sciences or further mathematics. So maybe the first thing to consider here is the example on this page. And this example is going to give us a motivation for why we might want to take a limiting process. And what we're really doing in the background is a derivative, but we won't get to that until a few sections after this one. So for now, let's just work through the example, and we'll talk about limits for the rest of the section, and eventually we'll get to the point where we really want to find a derivative and we're ready to talk about it. So the example says, use the formula s of t equals 4.9 times t squared for distance s and time t to determine the velocity after 5 seconds of falling of a ball that's dropped from the top of the stratosphere tower. So we're going to go to the top of the stratosphere. We're going to drop a ball. We want to know how fast that thing's moving 5 seconds after it's falling, right? Just out of curiosity. Really, generally, we might want to know how fast it's falling after any number of seconds. And what we want to know is how fast it's falling in that 5th second, in that instant moment of time. But what we find just using algebra in the example below is that we really we can't do a lot to figure that out because we just don't have all the machinery in place. So this is really the point of the limit. The one thing we can do algebraically is to say this. Well, if we know that this is the distance the ball has fallen after t seconds, well, then we can calculate the distance the ball falls after 5 seconds, and then divide that by the amount of time that's gone by, which is 5 seconds. And then we'll be able to get the average speed from 0 seconds to 5 seconds. And then we'll just assume that, we can use that as a stand-in or an approximation of how fast the ball is falling at 5 seconds. That should feel maybe insufficient, right? But it's as close as we can get with just algebra. So once we know the limit, we'll be able to do better. So as I said, we'll use this formula. It's the distance the ball has fallen after t seconds. Remember that speed is the change in distance over the change in time, or distance over time. In this case, position after 5 seconds minus position after 0 seconds. This will give us the distance the ball has fallen. And then 5 seconds minus 0 seconds. This is the change in time. This is from the 0th second to the 5th second. So that's going to be 5 seconds that have gone by. And what do we have in the top here? We're going to have this function of 4.9 times 5 squared is this term. And then we'll have 4.9 times 0 squared comes from this function, applying s of t once again. So the one on the right of the minus sign is just a 0. The denominator is just 5, right, of course. And this one takes a little simplification. 25 times 4.9 is what we'll want to do eventually. But notice that the only term left is 4.9 times 5 squared divided by 5. So down below, we can do a little simplification here, and we won't really need a calculator. 5 squared over 5 cancels out one factor of 5, so we're left with 5 to the first power in the numerator, just a 1 in the denominator. So this is 4.9 times 5. Because maybe you check that algebra or arithmetic on your own. 4.9 times 5 comes out to 24.5, as we see right here. So it looks like the ball travels at 24.5 meters per second. That's its average speed from time 0 to time 5. Another way we might do it is say, well, that doesn't feel sufficient, right? Maybe we would do time 4 seconds later, and then 5 seconds later. And then we'd get the average speed from the 4th second to the 5th second. And that might be a little bit more accurate, right? And it'd be 5 minus 4 here, because it would be closer to the 5th second. We wouldn't be averaging all the slow velocities that occurred close to 0, right? Or maybe you didn't like that. You could do 4.5 here and here. 4.5, the 4.5 second to the 5th second, right? Or 4.9 seconds to the 5th second, right? And you start to see the process. This is this limiting idea. We'd pick a number closer and closer to 5, and then maybe we'd get a more and more correct approximation of the instantaneous velocity of the ball. But we don't quite see what we would need to do in order to get the actual instantaneous velocity of the ball. And this is where the limit comes in, right? So let's have a look at an example of a limiting problem, okay? So we're going to think about this with just another function. It's not too different. It's x squared minus 2. It's also a quadratic function. Its variable is squared. And we're thinking about the behavior of it, or the output of the function's values for x values that are near 2. So in other words, we're going to do that process I was talking about. We're going to approach 2, say from 1 to 2. That's a reasonable average of what's happening at 2. And then 1.5, and then 1.9, and then 1.99. But instead of doing an average velocity or anything like that, we're just going to see how the function behaves when we plug in numbers that get closer and closer to 2, because we're just curious to see, what this intuitive idea of the limit of this function is as x approaches 2. So a lot of you would probably look at this and just say, well, okay, I want to know what this function does near 2 when x is near 2. Well, how about I just plug in x equals 2? And I get 2 squared, which is 4 minus 2, and overall that would be a 2. And you'd say, well, yeah, it must probably approach 2. It's not always the case. The function has to be continuous for that to work. And I believe we'll see that in the next section. If not, we'll see it very soon in one of these sections. So continuity is a nice property of functions that we'll get to soon enough, but it's not always very reliable. So you can't just take this 2 and plug it in to any function, all right? So for now, let's just, even though we can do it for this one since it's continuous, let's just go ahead and run some of these numbers through this function and see what we get out, right? So if I plug in x equals 1, I'm going to apply this function to it. 1 squared minus 2 is negative 1. There we go. 1.9, I'm going to step that much closer to 2. I'm going to skip 1.5, right? I want to get as close to 2 as I can here. And with a calculator, 1.9 squared minus 2 is 1.61. You can check that on your own if you like. And then we'll go to the next value. 1.99, when we plug it into this function, gives us 1.9601. Okay? 1.999 is probably a number that's even closer to the value 2, right? It looks like these numbers are converging onto the value 2. You might try 1.999 or 1.9999, right? Just to see that the next number in this sequence, without plugging in 2 itself, is a number that's closer to 2 than the ones that came before. Similarly, from the other side, we start at 3 and we plug 3 into this function. That's 9 minus 2 is 7. It's pretty far from 2. That doesn't seem very good, but we try 2.1. And when we do that, we get 2.41. Again, plugging in 2.1 into the function. Then we plug in 2.01 into this function for x, and we get 2.0401. When I look at this sequence of numbers, I'm moving these values closer and closer to 2, and it just so happens that these numbers are getting closer and closer to 2. Now, the fact that we're approaching 2 with our x values, and our function is approaching 2, it's also is just a coincidence, maybe a confusing coincidence, but they don't have to be the same value here and here. This could be x approaching 2 and the function itself approaching 4, and you see similar results. So if we're more or less convinced, maybe we try 2.001 and we get a number that's even closer to 2 than this one. We're more or less convinced of this. We can kind of walk away at this point and say, well, the limit as x approaches 2, reading this operation here, of the function x squared minus 2 is equal to 2. So in other words, this whole equality that we're lining up right here with these symbols is telling me what this table was suggesting. It says that as x gets closer to 2 from either side, the function itself gets closer to 2, right? And this idea of a function approaching something is the limit of a function. It's got a name and we call it the limit of that function. And that's exactly what this object right here is. So it has a more exact definition, and I might be able to go over that in this video at the end of these notes. If not, I'll make a separate video for it, or I'll just cover this in class directly, or cover that in class directly. So down below, we have a definition for the limit. It'll only be a little bit helpful, but let me read it anyway. Suppose f of x is defined when x is near the number a. So a is playing the role of this 2 from above now, right? So some numbers, f is defined when x is near a. It might not necessarily be defined at a, right? And that's the key thing about a limit. So in other words, it's defined on some open interval containing a, except possibly at a itself. So it could be defined for all these numbers, but not 2, right? That's the idea there. So we'll write this limit as x approaches a of f of x equals L, read it just as suggested below. If we can make the values of f of x arbitrarily close to the limit L, that's that number on the right, by taking x values sufficiently close to a, that's the number that x is getting close to, but not equal to a, right? So in other words, we can get, this is our L, we can make this function f of x as close to this number 2 as we like, this limit L equals 2, by taking values of x that are sufficiently close to a, right? The value that x is approaching, without ever actually plugging in for this value a, or in this case 2. So that's the idea. It's really confusing to look at it right now. In the end, we're going to get to a point where we can do a lot of work with limits, where we'll have a rule where you just plug this thing into the function and it'll work out fine. It won't always do that, so you really do have to pay attention and learn these steps for general problems, but in a lot of cases, we'll be able to work with continuity. So let's approximate a limit using a table of values, right? This is the only tool we have so far. Like I said, there is a precise definition of this, which I'll either cover in class or a separate video. But for now, let's go ahead and use our intuitive definition, right? So they ask us to take the limit of this function as x approaches 0. So what we're interested in is what we don't want to do is plug in x equals 0 to this function, right? Because for one thing, the limit tells us not to do that, right? We can only take values close to 0. We can't plug in values we can't plug in the value 0. Okay. Moreover, we can't plug in the value 0 in this case because the function's not defined there, and we'll see later that it's also not continuous there since it's not defined there. Again, continuity is a later concept, but it's nice to think about it now. So this one we're forced to actually use values near 0, but not actually equal to 0 because that would make the function undefined. So anyway, let's go ahead and start. When I plug in 1, I might need a calculator to do this, but I have 1 plus 4, that's the square root of 5 here, minus 2 divided by 1, and it looks like that, thanks to a calculator, comes out to this decimal, rounded to the 5th place. Now 0.1 plus 4 gives us 4.1, square root of that, whatever that number is, minus 2 over 0.1. And the calculator tells us that that's 0.24846, again, rounded to the 5th decimal place. And you can continue to check 0.01 is this in the function, 0.001 gives us this through a calculator, and so on. And we get to this step here, and we compare it to this one, right? We're comparing 0.001 and negative 0.001. So the idea is this: in between these two x values, right? In between here is the value of 0, right? We never plugged in 0, but we plugged in numbers that were pretty close to 0. If you're not convinced, try 0.0001 and negative 0.0001. But I think with these numbers on the table, and you can plug those in if you like and check with a calculator to see what comes out. But I think if we look at these numbers on the table, we're pretty well convinced. It's not mathematically sound to just assume this, but it's pretty convincing that this limit seems to be approaching 0.25 or 1/4, right? Again, these two evaluations should provide further evidence to that, even though it doesn't provide a full proof. but it should definitely convince us that we can probably walk away from this one and conclude that the limit as x approaches 0 of this function is equal to 0.25, or seems to be approximately 0.25, or 1/4. Right? So we're saying approximately because that's the best we can do with what we know about limits so far. We can't prove it's 1/4 yet, but it appears that it's approximately 1/4 thanks to our analysis here. So that's how we go about doing these. Here's an interesting problem to have a look at. Of sine of x over x, and we're taking its limit as x goes to 0. So sine of 1 divided by 1, and then sine of 0.1 divided by 0.1, and so on, right? And we can do that from the negative side as well. It looks like the first couple of these are done. And what I'll do is leave the rest of these for the reader or the student to try out. Plug these values into sine. Make sure your calculator's in radians. You do sine of 0.001 and sine of 0.01, each divided by x again. And what you see for a while is that these numbers are pretty similar. But it'll turn out, and we'll see this later, that this function actually does have a limit, and this actually won't quite bring us to what we expect it to be. So at least from the table, right? It won't bring us to what this value actually is, unless maybe we got really, really small with these decimal numbers. But anyway, nonetheless, make an approximation for this, and we'll see later on what this actual limit is in its exact form. So that's an exercise for the student. Now, what we've talked about so far is a one-sided limit, but we seem to be approaching the limit from either side, right? We approach 0 from the positive side, we approach 0 from the negative side, from the right and the left, right? Same here. We approach 0 from the right, we approach 0 from the left, right? And that's to talk about the limit as x approaches 0. So we always want to think about these limits coming in from both sides, but that's only if we're talking about a general limit, right? In this case, we could talk about the left-hand limit, right? Which is given here, the limit as x approaches a from the left, right? So in other words, a from the negative side. Note that if a was sitting on a number line, it would look something like this, right? We'd have a right here. The left side of it would be here. The right side would be here. That's the way we'll treat it. It's not necessarily negative numbers over here. It's just numbers that are less than a, or on the left side of a, and that's what we just denote that with a negative sign. Numbers that are greater than a are just denoted with a positive sign. So if we're approaching a from the left, we're going to pick values that are slightly smaller than a, but close to a in value, and we're going to get closer and closer to a. If a was 2 again, then we'd do 1.9, 1.99, 1.999, and that would be approaching a from the left. If we wanted to approach a from the right, then we would come in this way, and that would be, if a was 2, it'd be 2.1, 2.01, 2.001, and so on. So that's a left-hand limit, and it's basically the same language as the two-sided limit. Here's a connection between the left-hand limit and the right-hand limit, and the limit we've already talked about, which is this one, the limit as x approaches a, and that's the following. This limit is this equality here, the limit as x approaches a of f of x is equal to L if and only if. Now this language means this. It means that if this is true, then these two things must be true. And then vice versa, if these two things are true, then this must be true. So that's what if and only if means, right? It's an equivalence statement, or a logical equivalence. So if we know that the limit as x approaches a from the left of f of x is L, and we also know that its right-hand limit, the limit as x approaches a from the right of f of x equals L, then we know that the two-sided limit, the limit as x approaches a of f of x is equal to L. Similarly, if we know this one, then we know that both of these must be true as well. So that's a key thing to know about these one-sided limits connected to our two-sided limit or general limit. So let's look at these graphically, right? That's enough sort of theoretical stuff and notation. Let's get into maybe some more intuitive pictures of these things, all right? So they ask us to use the given graph to state the value of each quantity listed. So all these quantities are limits, more or less. A couple of them are evaluations of the function f, places where we plug in a number to f's argument. So let's see what we have. The limit as x approaches 2 from the left of f of x. So this is our function graphed here, y equals f of x, right? So x approaches 2 from the left. So what I'm going to do, I find 2 on the x-axis. And then I'm going to think about what happens immediately left of 2. Well, on the left-hand side of 2, it looks like the graph is approaching a function value or a y value of 3, right? This line is approaching 3 as we move x towards 2. So our limit as x approaches 2 from the left is 3. That should make sense. Next up is this. What happens if we approach 2 from the right? What is f's behavior? What does its graph do as we approach 2 from the right? Well, here's 2 again, and I look to its right, and I move towards 2, and I'm on the function, and it looks like it moves down to, well, this is a y value of 0. And it's on the x-axis. So it looks like as we approach 2 from the right, our limit value is 0. Okay, now what's the limit as x approaches 2 of f of x? Well, let's go back to a quick theorem that we just saw, right, on the previous page. And that's this. This limit is equal to L if and only if this limit equals L and this limit equals L. These are the same values. This is L and this is capital L. This is not capital L and capital M. These two values have to be equal, right? That's what this rule is telling us, right? Not only do these two limits exist, but they're equal to the same value. They're both equal to L. Well, the problem with this limit here, when I ask for the two-sided limit, is, well, then I check it. Say, okay, what is my left-hand limit? It's 3. My right-hand limit is 0, but those two things aren't equal, right? 3 is not 0. The left-hand limit is not equal to the right-hand limit, so it doesn't have a two-sided limit, right? In other words, if we said this, well, it approaches this from here and approaches this from here, we'd see that, well, it's not approaching the same values. As we approach 2 from the left or approach 2 from the right, it's not connecting. We're not going to the same y value, so there is no limit or no two-sided limit for this function. So this one does not exist. D and E stands for does not exist. I think we remember that from algebra most likely. Now here's a weirder part. What's the function evaluated at 2? In other words, what's f of 2? Well, you go to the graph of the function and just look, right? Well, this thing, I don't need to do any limit tracking or anything like that. Here's 2 for x, and the graph is, well, it's on the x-axis when x is 2, so that's y equals 0. So f of 2 equals 0. And so here we are, f of 2 is equal to 0. So we kind of got that one pretty easily just by looking at it. Interestingly enough, it's equal to the right-sided limit, just to note that. Now, what's the limit as x approaches 4 of f of x? Okay, well, they ask us for the two-sided limit. We should probably check both sides though, right? So as we approach 4, it looks like from the left, we get a y value of 4. As we approach 4 from the right, this is this way, moving towards 4, our y values move towards 4 once again, right? So let me do that one more time. Approach 4 from the right, and our y values approach 4. Okay, and then similarly, when we approach this 4 from the left, right, we approach 4 also. Okay, as we move to 4 from the left, we go to 4 on the y-axis. So the limit And so both the left-hand limit's 4 and the right-hand limit's 4. So our two-sided limit is 4 because they're equal and they exist. So it all matches up. Now, what's the value of the function f at 4? Well, there's a hole right here, right? So when we plug in 4, the function doesn't give us 4. It gives us this point, this value of 5. Okay? So for a function like this, we can't just find its limit by plugging 4 into it, right? We see immediately that that wouldn't be correct because they're not the same value, right? So this function happens to not be continuous. And I do believe in the next section we'll talk about continuity and start to get some rules for how to recognize it and be able to use it. So there we go. And there are several examples like this in the book and the exercises, and it's definitely worth spending some time on graphically understanding these. This is one of the best places to get to know a limit is by looking at graphs first. Then you can go back to something like this precise definition of a limit. And I'll save this either for class or an additional video to come along with this. So for now, remember that there's one student exercise to do. See if you can figure out what this limit might be and look at a couple of these graphs to really get the hang of what's going on with these limit evaluations. And then I'll meet you in the next video, which is, well, it may or may not be continuity, but we'll see then.